Now let's look at this existence problem. Okay? Existence of n disjoint line segments. Here, from the figure, you can see we have n red points and n blue points spread pretty much randomly on a plane. The only restriction is no 3 points are collinear. That means we do not allow 3 points on the same line. Okay? Yeah. Then we want to show this result. We can find n line segments. So each line segment, we take one blue point, one red point, we connect them to get one line segment. So we can get n pairs of red, blue points, okay? And connect them to get n line segments. So now the conclusion is it's possible to find those n line segments such that no 2 line segments have intersection. Okay? Show that. Okay. Yeah. So it's pretty challenging. Yeah. So let's do some analysis. Okay. Again, so let's examine the uncertainty. So a lot of uncertainty here. Okay. First, locations of the points. No specific, precise descriptions on locations of the points. Where are they? Okay. So nobody can tell you exactly. Okay? So that's one of the hard things. Second, selection of red and blue points. How do you pair those red-blue points? Okay? One red point is associated with one blue point to form a pair, and you get n pairs. Okay? There are so many different ways. Okay? If we use some basic combinatorial knowledge, we will have this formula. 2n choose n. Okay? This formula. So, like you see here. Okay? In order to give you the sense of how large this number is, so I calculate two numbers for n. The first one, n equals 20. Then we'll get this number, okay? About 180,000. Second, n equals 40. So this time you will get a 12-digit number. It's pretty big. Yeah. So that's why. So the reason I show you these numbers is the total number of pairs could be very large. So that makes the problem hard to solve. Okay? The third uncertainty, how to pair these points. Okay? Suppose you determine n blue points, n red points, their locations are fixed, but you still have many ways to pair those points. Okay? So here we can do some simple calculation based on, counting, product rule. Yeah, product rule for counting. Okay? Yeah. So first, let's think in this way. Okay? Among those n red points and those n blue points, first let's select the first pair of points. Okay? Yeah. How many ways do we select from n red points? That's n. Similarly, there are n different ways to select from n blue points. So that's why we have n squared, n times n, product rule. Okay? Yeah. But that's for the first pair. Okay? For the second pair, among the remaining n minus 1 red points, there are n minus 1 choices. And the remaining n minus 1 blue points, n minus 1 choices. That's why we have n minus 1 squared. And so on. Okay? So we multiply all those numbers. Okay? But there is an order problem here. Okay? When we select those pairs, because at the end, the order of the pairs is not important. Which one is the first pair, which one is the second pair, the third pair, it's not important. So we need to remove the order. Okay? So that's why in the denominator we divide it by n factorial. Because there is an n factorial. So no, for the same n pairs, okay, considering the order, there are n factorial numbers. Okay? So that's why we divide it by n factorial. So finally we get n factorial. It's still a big number. Okay? So when n is large, it's a big number. So that's why this number 3, pairing those points, it's hard. Okay? Too many cases. Number 4. Locations of n-line segments. Hard to describe. Okay. So that's why all these 4 things make this problem relatively hard to solve. Okay? So we have to find some smart way to handle all the complexity. Okay. All right. So next, so let's try to understand the existence problem a little bit. Yeah. This is existence problem. So what's that? We only need to show existence mathematically. Okay. What do you mean? Okay. Show existence mathematically. Yeah. You do not need to really find those pairs. Without finding those pairs, you can still show existence mathematically. So the reason is simple. Yeah. Let me use a simple example to explain that. Okay. So there is a result. There exists infinite many primes. So you can show there exists infinite many primes. So here it's an existence problem. Okay. But in this problem, nobody can explicitly find infinite many primes. Okay? So nobody can write formula expressions to provide infinite many primes. So that's extremely hard. Okay? Yeah. But there is a way to show existence of infinite many primes. Okay? So here we do not show it. Yeah. Okay. All right. Okay, so another issue. How fast to find those pairs, it's not important. So that means the performance of the algorithm is not important in this problem. Okay? Because that's a computer science problem. Okay? So here we are working on a math problem. So we do not consider the performance of the algorithm. Okay? So all right, so that's about understanding of existence problem. So let's continue to try to solve it. Okay? All right. Although this problem looks pretty complicated, but there is one simple principle that can be used to solve this problem. Okay? The principle is so simple, I believe everybody here knows about it. Okay? So if you sit here, watch this video, I believe you know that fact. Okay, what's that? Okay. given given finitely many real numbers. Finite, okay? Finitely many real numbers. There exists a smallest one. This fact, so simple. There must be a smallest number in this finite set of real numbers. So that's obvious, right? But this principle is very important. Okay? So there is a name for it, extremal principle. Okay? So it is an important result in discrete math. Okay? So here we use it. All right. Here we use the real number version because there is an integer version. So not related to the problem here. So we do not talk about that. Okay. All right. Suppose we have m real numbers, R1, R2 through Rn. So that's a finite number. Okay. And that number could be a big number, very big. No matter how big it is, it's finite. So we can apply this extremal principle for, real number versions. Okay? Real number version. Okay. So the next step, let's use this extremal principle to solve this problem. Okay. All right. So let's consider all sets of pairs. The general expression. Let's take one general set of m pairs. Okay? Yeah. So R1, B1, so one red point, one blue point to form the first pair, second pair, and so on. Okay? Yeah. So it could be a big number. Okay? Yeah. But finite. So definitely it must be, actually the finite, what I mean is the total number of such sets, that is a finite number. Okay? The number of sets, that is finite number. Okay? Okay. All right. So now let's connect n pairs of points in each set to form n line segments. So that's obvious. Okay? Just connect them. Okay? Then we calculate the sum of the lengths for these n line segments. So there is a real number as the sum. Okay? So let's denote by S. Okay? Yeah. So let's list all the sums. It's S1, S2 through Sn. Okay? All the possible sums we can find. Okay? That's a finite number, right? Not infinite, finite. Okay? Yeah. So if that's a finite set, then we can apply extremal principle. Okay? So we can get a minimum Sk. Okay? That's important. Okay? That Sk actually gives us the solution. Or, to be more precisely, the set that corresponds to Sk would be a solution. Okay? Yeah. So when we have many solutions, the solution does not have to be unique. So we just want to find one of the solutions. Okay? So we claim the smallest Sk corresponds to the solution set. The set for the solution. Okay? All right. But we need to prove it. Yeah. So it's not trivial. Okay? So we need to spend time to prove it. Okay? So the next step, let's show the selection is a solution. Okay? Yeah. Suppose this is the selection. Okay? With minimum total length. Okay? Sk. Yeah. In order to show there is no intersection between any two of the line segments formed by the pairs in this set, we need to use contrapositive proof. Okay? Yeah, because it is very hard to prove directly. So we need to use that contrapositive method. Okay. All right. So we make assumption. Okay. Assume that there are two of the line segments that intersect at a point. Okay. All right. Assume that we want to derive a contradiction. Okay. Yeah. So, like we have here. So in the figure, okay, our goal is to derive a contradiction. Okay. So then we can prove the result, the claim. Okay. All right. So next, contrapositive proof. Okay. Yeah. So let's draw these two line segments like this. Okay. They have an intersection. Oh, okay. Then we connect these two pair of points, dotted lines, to form two triangles. Then we can use some simple result in a triangle. In triangle, we have a triangle inequality. Triangle inequality. So that's the sum of any two sides is greater than the third side. So that is very important for this problem. Okay? So we use that. Okay? First, in triangle OR1B2, OR1 plus OB2 is greater than R1B2. Okay? Yeah, sum of two sides is greater than the third side. Okay? Similarly, in triangle OR2B1, we have OR2 plus OB1 is greater than R2B1. Let's add up these two inequalities. We get R1B1 plus R2B2 is greater than R1B2 plus R2B1. That's very simple. Okay? With this inequality, we can make conclusion. Okay? All right. So let's look. With this inequality in our mind, now we want to modify the original two pairs. Okay? So let's disconnect R1B1 pair and disconnect R2B2 pair and reconnect them in this way. Okay? Connect R1B2 and R2B1. Okay? Because after this modification, we will get a smaller sum of line segments for those two pairs. Okay? Yeah. To be more specific, the original n pairs we list here, their modification, we switch B1, B2 in their corresponding pairs. Okay? After this switch, based on our analysis above, more specifically, that R1B1 plus R2B2 is greater than R1B2 plus R2B1, that will give us the sum is reduced. The sum of all the lengths of all the line segments reduced. Okay? So if that is reduced, it contradicts the assumption that SK is the smallest. Okay? Yeah. The SK is smallest. Why? You can still reduce it. That's a contradiction. Okay? That means SK is not the smallest. Okay? So that tells us the assumption here is not correct. The assumption that there are two of the line segments that intersect at a point, this is wrong. If this is wrong, then the conclusion is no intersection. So we prove the claim. That means we show the existence of m pairs of line segments, or m pairs of red-blue point combinations such that the line segments formed by those m pairs do not have any intersection. Then we solve the problem. Okay? Yeah. We finish it.